Obviously yours might look different than mine if you guys draw them. But just to remind you guys what a chord looks like, what a tangent looks like, what a secant looks like. We're going to be using those all today in our notes. So, and the rules we're going to look at, or like the drawings we're going to look at, are going to seem really similar to the ones we were just talking about, like the half where you add the two together. But now rather than talking about the angles, they're going to talk about the length of the lines. So, for instance, a chord stays inside the shape. So a chord would be, basically it connects 2 points on the circle. So like AB here would be a chord. Now when we're talking about a chord here, we'd be talking about the distance from A to B. So like think about it as I would be able to measure that. I could measure that distance by taking out a ruler and measuring it. So they're not talking about an angle here, they're just talking about the length of that chord. A tangent line is usually outside the circle, but it touches the circle in just one spot. So, and again, it's been a while since we talked about this, so this is kind of a good review going into today. So a tangent line is outside the shape. So it hits the side of the circle just one time. So the tangent can either be a line or a segment. So you can either say the tangent keeps going forever or it stops. And this is supposed to look straight. If mine doesn't look straight, pretend it's straight. And then our last one is a secant. Okay guys, so secant goes through our shape and it hits the shape twice. So a secant's kind of a chord that keeps going. So in this case, like I don't know if we just want to go like all the way through here.
Crazy.
Now notice none of these need to go through the center of the shape. They, I guess like a secant probably could. A chord probably could, but typically they're not going to be going through the center. So the last thing we learned about on our sheets was talking about the angle measures and the arc measures. Today we're actually going to talk about the lengths of these segments inside our circles, outside our circles. So when we're talking about segments of chords, we're talking about the length of the chords, and this time it's inside. So again, like just make sure it's clear. We have a formula that goes with this shape. Maybe I'll write it off to the side here. Maybe I'm going to put it on my board over here. Is if I'm talking about the angle, it's half of the two arcs added together. So this formula is talking about if I was talking about this angle, so this angle here is the two arcs added together. That's not what we're going to be talking about today. What we're talking about today is the lengths of these little like lines instead of angle measures. So that's different than what we learned about last time. So there's different things we're measuring here. So they're going to talk about the lengths of these little chords, or the pieces of these segments. So basically this AB is going to get multiplied times the other half of this line. So times BF. And that's going to equal, and so again, if you like different colors, that might not be a bad idea. That's going to equal the other line, like the little pieces. So EB times BD. So I'm going to show you guys a little example of this. So this is what this drawing looks like here. Now, initially looking at it, you might just say, oh, that other one, that little other piece should be 7, because the one is 10 across, the other one shouldn't be the same. Not necessarily, we don't know that for sure. So we're gonna do this little example that goes with this idea. So, in this case, we have this 3, and it's gonna get multiplied by x. So the same line gets multiplied together. It's kind of a crazy formula how this works. You know, I don't know who came up with it, pretty like kind of clever that this works. And that's going to equal the other 2 parts multiplied. So this 4 times the 6. Well, so I have 3x equals 4 times 6, so 3x equals 24. So I divide by 3, and so we find out x would be 8 in this case. So that's just a little example to go with this problem. Okay. All right. So our next one here. Okay, so, and again, we'll end up putting this on our chart. We might even do that today, just so we can get that chart taken care of. Is now we have secant segments, but they're outside the shape. So notice these do not intersect on the inside. So what we do in this case is this little part, this little AB, and I'm going to call that the outside part. Not just the inside, but the whole thing. And again, I don't know who came up with this and figured this all out. It's kind of crazy, but it works.
A really smart guy.
Yeah, really smart old guy.
Like me.
He probably had long hair and a long beard. And that's going to equal basically the same thing on the other
I
side.
really see the receding slope. So again, I'm going to show you guys a little example of that. Oops, sorry. Okay. So here's our example that goes with this one. Now, this is a little bit tougher than the last kind. You have to remember that you have to do the whole segment. So we start with the outside part. So the outside part in this case would be 6. And, oops, I need to use red instead. Sorry, I want to color code here. We're going to do 6. That has to be multiplied by the whole segment, which would be 15, 9 and 6 together. Okay. And we're going to set that equal to, again, the outside, which is this little 5, times the whole segment. What's tangent going to be in this case?
5 plus x.
5 plus x or x plus 5?
It's 5.
Same thing.
Yep. She says the same thing now. Same thing, buddy.
Okay. So that's a little bit trickier, so make sure you guys are careful with that. We're talking about the whole thing versus just the inside. So now we go ahead to solve this. So 6 times 15, anyone help me out here? 90?
Yes.
Yeah.
We'll do a math.
Equals 5x.
And then 5 times 5 is easy. Okay? We have to distribute there. I'm going to move the 25 back over. So we have 65 over here equals 5x. So x is going to end up being 13.
15. Yes.
Okay? So again, just a little example that goes with that to be able to reference that for what we're working on here today. All right. Then our last rule for today is now taking a tangent and a secant together. So noticing the difference between these two. The secant, both of them go inside the circle, whereas this one, a tangent just stays on the outside. So there's a different rule with this one. So, try to explain this one. So this one, in this case, normally we take the outside and multiply by the whole thing. Well, a tangent only has an outside. So we're going to multiply that by itself. So we're going to take JK and square it. Multiply it by itself. And that's going to equal the same way we did the other part. So the outside and then the whole.
Don't dare.
All right. So we'll write this rule down, then we'll take a break. On the break, yeah.
Still, no, there's 2. There's still. There's 2. There's 2.
All right. So, which one's the tangent in this case, you guys? The 8 is our tangent. So that's the part that's going to be squared. So we're going to do 8 squared, because it doesn't have pieces of it. So you just have to multiply it by itself. That's being set equal to the outside times the whole. And so again, this comes a lot like the last one. So 6 times x plus 6. So this ends up being 64 equals 6x plus 36. It's 8 squared, 64. What's that? 28. Supposed to be a decimal.
4.6 repeated.
Okay, who's the here?
So 4.6 repeated, so I'm going to call it 4.7. Okay. All right, so we're going to take a little break before we do some more practice problems with these.